let us start off. And what I'll do for this 1 hour is I'll go through case studies and now start getting more into machine learning, right? And hopefully set up things well for Elias. So what I'll do is we'll finish the example on Google mobility and daily cases, COVID cases in Toronto. Then I'll discuss another paper of mine, which looked at US data. But the US data, the methodology I used was, I beg your pardon, clustering, which is hugely beneficial and so easy to code. So Elias will be talking more about the coding. I just want to show you what you can do with machine learning algorithms such as clustering, the usefulness of it, okay? So, and then what I'll do is that I'll go into models which use one zero binary variables, because those are also the foundation of machine learning. You know, you have probe and logit models. So what are they? So hopefully all that will start getting into the world of machine learning now, based on what we know of regression analysis, and it'll really smoothly flow into our next sessions later in the afternoon. Okay, so let's start with, okay, the example. So, okay, so Ethan, just checking you can see my Learn site.
Looking good.
Okay, great. So the idea out here is to look at to come up with a model that can explain the spread of COVID-19 on a daily basis in Toronto. And what we did is that you see the basic model we've come up with. The dependent variable are daily cases. And of course, a significant explanatory variable is that whatever happens today is a function of what happened yesterday, and along with different mobility variables like Google mobility at retail outlets, workplaces, and groceries. Okay, so as I said before, these are all Google mobility data. They were collected by Google. They're made available publicly, so there are no issues accessing the data, and they're available. The neat thing about it is, at least for Ontario, excuse me, they're available at the daily level for public health units. So we're looking at Toronto. Now, we're also going to do some coding, okay? So here is the simple coding. I've shown this to you before. As opposed to showing it to you in my R console, I think it's well laid out on the Learn site, which I'm using. So again, we're just reading it a simple data file and then summarizing it to look at the means and medians and the min and max to make sure the variables look all right and we've read in the data properly. So I can't tell you how many times that I've seen so many regression analysis just go wrong because somehow the coding software hasn't read in the variables properly. So it's really, as far as digital hygiene, it's really important to just do this command as a start to make sure that the variables look like it should look like, okay? And if there's any outlier, then you need to go back, or something which looks unintuitive, you need to go back and check if you've read the data in properly. Okay. Now, what I want to do is that I will again use the core plot command, which I showed it to you earlier. And let's just take a look at the output. Here we have cases, and we want to see what mobility variables are correlated with cases. And unsurprisingly, cases today are very highly correlated with cases yesterday. Now, in terms of population mobility, what seems interesting is that you really don't see much of a correlation. I mean, these are really low values between retail and grocery mobility, mobility at retail stores and grocery stores, and cases. but work mobility, maybe slightly higher than retail, but it's the highest we've got. But again, not really overwhelming. But what's important to note is that sometimes just the way things are set up is that even though you might have, excuse me, very low correlation numbers, things might change when you include them all together in a regression framework model. And that's because in a regression framework model, what it does is that it takes into account the correlations between the different X variables. So what you can mathematically demonstrate is that variables which in isolation have low correlations, when you include them all together on the right-hand side, they actually might have a strong effect on your outcome variable, okay? But before we look at the regression, what we want to do is that we want to look at some very simple plots. So again, this is just a very basic plot command. And you look at this, and again, it's really nice visual, so easy to generate. And you see, I start off by looking at the trends in daily COVID-19 cases for Toronto over time, and the y-axis is the number of cases, and here are the months for 2020. So we see the first wave, which we know historically was nothing compared to what happened afterwards, okay, in terms of the incidence of the disease. But in terms of mortality, of course, the first wave was the scariest. But we're just looking at the number of cases here. I also now want to, so in this coding, I'm just quickly skimming through it because I want to get to quite a few concepts in my 1 hour, is that here are other visuals. So what you want to do is that you want to look at just the raw figures and draw some idea on relationships based on visualization. And the way I look at it is that when we had, things are different across waves, but when we had this deep incline, that's one way to look at it. Did we also have higher mobility? And we do see that. And what's interesting is that mobility, as measured by Google data, retail mobility started going up, but when cases started really spiking, sometime October, they started dropping, right? People started getting more and more cautious. Now, with grocery mobility and the spikes are weekends, grocery mobility, what's interesting is that relative to retail mobility, grocery mobility stayed relatively constant in 2020 towards the latter part. And that's to be expected because groceries and pharmacies are necessities. I mean, irrespective of whether cases are going up, you have to go to the grocery store to get food. And this is just very spiky because it's work mobility, it's holidays and weekends. But you definitely see, if you look at a trend, you see there's an increasing trend, more people going to work and staying at work. Okay, so we're different X variables. The question now is, what was the most significant, right? That's what we can ask through regression analysis. So with a simple LM command, you see here, I'm looking just at the mobility variables. I don't have cases yesterday as a right-hand side variable, okay? But we'll get to that. So again, how do we diagnose it? Well, the R-squared is really small, 0.06, so there's not much this model is explaining. So the way you'd explain this model is that, the overall fit of the model, the way it's fitting the data is not good, okay? Really low. But controlling for that, are some variables significant? I mean, retail mobility is, and so is work mobility. The t value of grocery is pretty low, so I'm not going to count it. But work mobility, it, has the right positive sign. Now, if you recall what I said, what's really important is to have the right sign. And retail mobility perversely has a negative sign, right? That as more and more people went to retail outlets, restaurants, cases went down. Like that doesn't make much sense. Um, so it's picking up when you have a counterintuitive sign. Usually the reason is that you're picking up the effects of another variable, which could be included on the right-hand side, and it's not there. So it's more likely that this variable, retail mobility, is picking up the effects of something else. And that's also likely because the R square is so low. Now, what happens when we add another variable? So when we add the key variable here, which is, remember, the dependent variable are the number of daily cases of COVID. The key variable on the right-hand side now is, excuse me, the number of cases yesterday. So unsurprisingly, that has a huge effect, right? I mean, obviously, that if you live in an area where cases were high yesterday, it's quite likely that cases today will be quite high. Now, if you look at the R square, it's obviously shot up. It's now 0.97, right? And so the key question now is that when you have a model like this, where cases today are almost virtually explained exclusively by having another variable, which are cases yesterday, do any of the mobility variables, do they make sense and are they significant? And the answer is yes. So despite including the number of cases yesterday, what you find is work mobility has the intuitive positive sign that as more and more people went to work, cases started spiking up, and the t-stat is actually quite high, right? Retail mobility, the t-stat is high. It's above 1.95, but it's got a counterintuitive negative sign. So I'd be very careful of putting emphasis on this. So these results are obviously important. When you think about it, what we did is that we matched data sets, right? We pulled in data from different sources, from the Ontario Public Health website. I downloaded data on daily cases in Toronto, and I matched them to measures of population mobility. And you definitely see a relationship between population mobility. And I should have, sorry, I do beg your pardon, I should have been more specific that these, the number 8 out here refers to the fact that I'm looking at not mobility today or yesterday, but these are mobility values 1 week ago, 7 days or 8 days ago, because there's a lag between spikes in people getting together in mobility and the infection, when the infection starts. So in my research paper, I put in a lot of different values, 8, 9, 10 days, 12 days, but I found for some reason this value matching daily cases to what happened in retail outlets and workplaces 8 days ago had the biggest bang for your buck, right? The most significance and largest coefficient. So in my research, I used this basic model in forecasting. So that's where the machine learning comes in. So this is a very basic regression model, but what it provides information on are what variables are significant in impacting your outcome variables. And then you can use that knowledge to construct a machine learning model, such as gradient boosted regression trees, in predicting daily cases 1 week or 2 weeks ahead. So I published quite a bit of research on that, and I note that surprisingly, linear regression models don't do a bad job, but gradient boosted regression trees, which are a relatively straightforward machine learning algorithm, do a really good job in predicting or forecasting daily cases 7 days or 2 weeks ahead, but based on these results from underlying regression models. Okay, so that is the policy conclusion here. What I'd like to do then is kind of summarize that what you want to do and look out for in terms of using regression analysis. So here are some following steps. So these are the steps I use as a researcher. What I always do, the first step, is I clearly formulate my model, right? I specify what my dependent variable is. I decide based on theory, it could be economics, sociology, psychology, what the what the independent variables should be. And I write the model out. And when I write the model out, I use basic notation so people know what I'm doing, right? Then, as I said before, we use common sense, but your model should be grounded on academic research. And that's extremely important, that you know what other people did before you and you just build on that. It's a proper way to cite research, and but it's efficient also. Then with the coding, what I've tried to do is I've shown you some examples on what some basic data visualization methods can be. And what you should be doing is that even before you present the results of your regression model, you should show relationships between your variables, whether it's a correlation plot and or a combination with trend analysis through different graphs and scatter plots. Okay, so people have an idea of what to expect in your results before you show your regression model. I mean, it's not really a good thing if you're looking at some clear trends in your data and your regression models are giving you something totally different. It could be because you got a coding mistake. So that's something to be cautious about. Next step, when assess when assessing your model, check the R square. You need to have a model where the R square is somewhat respectable, right? That means the model is fitting your data well. And obviously, I'm speaking about linear regression models here. And in terms of respect, I'd say it depends on the nature of data. If you look at survey data across individuals in the same time period, it's typically 0.2, 0.3. That's low, but that's fine. But when you look at data that are aggregated, like what we've been using for provinces across years or city across time, then I expect something to be 0.6 or at least, and 0.7 is I'm comfortable. Next step, step 5, look at the signs of your explanatory variables. Again, do they have the expected sign? Because if you present your research transparently, the first thing someone will say, why does your right-hand side variable have the wrong sign? So that's something to be very cognizant about. Next step, it's not sufficient if your explanatory variable has the right sign. Is it statistically significant? So that's based on a t-value, and it tells you that if you keep repeating your analysis across many samples, on average out of 100 samples, how many times are you going to get a similar result? Okay, now, final thing, when you use a regression model, under some circumstances, and I'll get to that, yes, you can have causal effects. Now, economists have been really good at that. They use different methods such as regression discontinuity or difference in difference regressions. So I don't have time to get into regression discontinuity, but hopefully I'll have a few minutes to touch on difference in difference regressions. Now, when you use that, you can get a causal identification, but in the simple models I've shown you so far, no, they're not. These are not causal models. You can't infer causality. But what you can infer are very robust correlations. Okay, so these are kind of basic steps to keep in mind. Okay, now what I'd like to do is go to an article I wrote. Ethan, just checking with you, can you see the article on my screen?
Not at the moment. I'm still seeing Learn.
Okay, so I'm going to stop sharing. And what I'll do is I'll actually copy. It's freely accessible. So I will just put this in the chat. Yes, the paper's link, correct. So I put, this is a great question, which Stevens asked about stationarity. Yeah, so what you have to do about time series data is that you have to make sure that the data are stationary. So if the data are not stationary, basically you have something called a unit root. And what happens is that your standards just explode. I mean, you can't get anything reliable from your inference on that. So unfortunately, I don't have time to talk about that. But yes, Stephen, I did check for stationarity and everything was fine. Okay, now I have shared the paper here. And so this is where we get to machine learning. And in this paper, what we did is that we used particular type of machine learning called clustering. Now, clustering is one of my favorite methods. And the reason is that when you have a large data set and you're looking for patterns, now, in the data which I've shown you so far, it's just like 100 observations or something. So it's really small. So you can just look at trends across provinces over time, and you can get a feel of what's happening. Now, in this paper, which I've posted out there, I'm looking at US data at the county level. So I think there are about 1,800 counties. No, not 1,800, about 3,000 counties in the US. So I had a sample of 1,000 counties. And the reason I had a sample of 1,000 counties is that I wanted to look at these counties and look at trends in daily COVID cases and also daily deaths. And so studying the US was interesting as a contrast to Canada. And the data on daily COVID cases from the US came from Johns Hopkins, which is collecting the data. And the reason why I only could use 1,000 counties out of the 3,000 is that there were Google data specifically available for these 1,000 counties. So what I wanted to do is that I wanted to understand that when you look across counties and over time, then when you look at it through 2020 and 2021 on a daily basis, as some counties started opening up more and more relative to others, did you see a spike in daily COVID cases? And what made it difficult was the magnitude of data, right? So if you had maybe data for 300 days for each county, 1,000 counties, that's 300,000 observations. So not a huge data set, but it's really difficult to find patterns in the data when it's that large. So what you can do is you can use a method called clustering, and there are different types of clustering. And the most popular type is k-means clustering. It's just automatically set up. And what you do is that in this example, I had these different Google variables, as I showed you before, and at workplaces, mobility at workplaces, in retails, outlets, and grocery stores. And what I asked basically the algorithm to do, the clustering, is that based on distances between values, can you clump some counties together? So the idea of clustering is to find commonalities in trends when your data set is large. So in this case, I was asking the algorithm, and so this is a wonderful example of machine learning. I was asking the algorithm to look at these 1,000 counties over a year and look if you can divide them into different clusters based on Google mobility patterns, right? So I could have asked them just on the basis of one Google mobility variable, but I didn't do that. I said, like, here's all the Google mobility data. Tell me what you see. Okay, so now with that preamble, I hope not a ramble, a preamble, I can show you what I found. So this is a paper which is published with, again, few authors from University of Waterloo. Ken was a PhD student in health. Nilofer was a postdoc, and Plinio is my colleague in from the Faculty of Health, and he's also presenting in the conference tomorrow as I am. So now that I explained it to you, let me show you the visuals. Okay, so we did the clustering. Now the first thing is here, when you see this map, let me just check. Actually, I don't need this just now. What you can see is that these are where my data are from. So from the Northeast, from the heavily populated areas, you can see that I have a lot of counties, and I have counties in the West, kind of the South, and the Northeast. But in the open spaces of, say, Wyoming and Dakota, I just don't have a lot of observations. The Google mobility data um, wasn't that good in the sense that there weren't enough people there that they could preserve privacy. So that's why the Google data, mobility data, were not um, reported for areas where Idaho or Iowa and other areas, Dakotas, where um, population density was low. Okay, now what I did is that here's the demographic variables. So this is based on the 2016 census. So what I wanted to do, my research design was that I would run the clustering. I would see where counties fell into clusters, and then I looked for differences in terms of the demographic variables in 2016 that, what were the socioeconomic characteristics which defined areas with high mobility relative to low mobility. High mobility meaning a lot of people are just walking around and, going back their business of going back to shops and stores and work. Okay, so was it a question of income? Was it a question of race? Was it education? What was it? These are the technical details which are not important for this discussion. I'll just go straight into the clustering. So here, I will blow this up and okay. And I'll stop sharing. Ethan, can you see my blown up figure or you cannot?
I can only see the graph, I guess, the figure 5, and I can still see the sidebar on the left, so I don't believe that it's blown up.
Okay, just 1 sec. So what I'll do is I'll stop sharing and I'll try sharing again. I think it's this. Yeah. Now I believe you can see it, right?
You got it.
Okay, so this is for the retail Google mobility. And when the clustering analysis did is that it divided the counties, the 1,000 counties, in 1, 2, 3, 4 clusters. 1, 2, 3, 4 clusters. Okay, so when you look at the clusters at here, the dark red, this is where retail mobility was the lowest for some reason. They follow the same trends, but there was reduced mobility in this cluster relative to the other clusters and the blue one. Okay, so this is important to keep into account. And this is pretty much the case with the other clusters, that they follow a similar pattern, that the red cluster had the lowest mobility with respect to workplace and groceries also. And the data are from the beginning of the pandemic, from March 2020 to 2020 December. And you remember that this is the time where you had the US election. Okay, so let me show you something else. Now, on the other hand, I will quickly show you the residential mobility figure. Okay, so sorry, this is just taking me a few seconds. Okay, so this is a great figure. Now, it's flipped. It's flipped because I'm looking at the residential mobility, right? And what you see is that the red, this kind of cluster, is among the highest, right? So counties here, not only were they, you saw the least mobility at stores, but this is the highest mobility at home, meaning that people in these counties didn't really go out and they stayed at home. On the other hand, when you look at the blue mobility, there in these counties, people didn't stay home as much, relatively speaking, and they're, as we say, out and about. Okay, so we see these very kind of distinct patterns here. What does it mean in terms of demographics? So what it means in terms of demographics is the following. So Ethan, just checking, you can see my paper.
Yes.
Okay, so then what we do, machine learning also allows you to look at or compute what we call feature scores, that when we divide the data into clusters, what variables are the most important. And when you look at the data, what sort of pops out is education is important. Okay, so are some race characteristics, but education is definitely important. So therefore, what I did is that now I want to look at something very simple, the sample means of these key variables. So cluster 0 is where we had the most mobility. And cluster 3 is where we had the least mobility. What's interesting is cluster 0 had the highest proportion of elderly. But when you look at a pattern, it seems that education is extremely important, right? When you look at the clusters which had the most mobility of going out, these were the ones which, relatively speaking, had lower levels of education. You can see whites with less than college education, whites with less than high school education. They're much higher here as opposed to here in cluster 3. there doesn't seem to be a huge difference in public transit. What other variable, and you can also see that you see this a bit in less than high school education, but high proportions of less than college education. And you can see that's much lower in cluster 3. And you can also see that in cluster 3, which had the lowest mobility, the percentage of voters who voted for Clinton in 2016 were much higher. Okay, so it's not necessarily all clean identification, but you see patterns there. So now what I said that, okay, we've done that. Now, given that the data has been sorted by mobility, is there anything predictive what that happened in terms of cases and deaths? And we actually see that because, and here is a figure which I'll show in a new window. And I think this just summarizes everything. Okay, one sec, I'll just get rid of this. Sorry, just getting rid of some excess tabs. And there, here, there. So what you'll notice is that when you keep focusing on the clusters, the cases, here are daily cases, and they move, quite similarly till about October of 2020. And then you see a divergence. So what the story is that counties, the red ones, the kind of purplish actually, the counties which had the lowest mobility during the summer and early in the pandemic, the cases did rise. There's a common trend throughout the remainder of 2020, but in the counties where mobility were the highest, and these typically were counties where education levels were much lower and they're less likely to vote for Clinton in 2016, you can see the significant spike out there in daily cases relative to kind of the other baseline. And that was also the case with respect to deaths, which you see in the paper as well. Okay. Okay, so I'll stop here for a few. Oops, it's 11:39. Time flies. Does anyone have any quick questions or reflections on what I've shown so far with respect to clustering? Are we good? Did I manage to communicate through this example? Did I manage to communicate how you can use clustering for data visualization in data sets with a large number of observations? Okay, good. It was a good example. Okay, now we just have 20 minutes left. Okay, so what I would like to do now is go on to models with binary variables. So for that, I will go back to my Learn site and go on now to the third course. So the way our WattSpeed program is set up is that we talk about data, telling stories with data, and coding in R, and regression analysis in the first module. Elias, who will be teaching the second sessions today, teaches the second module of our program. And he really gets into Python and coding. And he gets into clustering, machine learning, some machine learning algorithms. But what he really does I mean, does everything very well, but he spends a lot of time teaching you how to take these large, unstructured, messy data sets and clean them up using Python. In terms of cleaning, I think Python's better than R, but I like R in terms of regression analysis, and that's just my preference. But the third course of the certificate is looking at, oops, sorry. So what we did was the basics. This is where we get into the more complex concepts, where we look at nonlinearities and we look at forecasting predictions, instrumental variables. And at this point, if you finish this course, you're really set to take more complex machine learning courses. Okay, what I'd like to do is touch on some of the concepts in module 5 of the third course, which is identification of policy effects. So in terms of policies, what happens is that there's some cases where it's very difficult to quantitatively model a policy. So what do I mean by that? What I mean by that is that our previous example in the morning was looking at minimum wage. So with the minimum wage, it's a no-brainer. On the right-hand side, you look at changes in the minimum wage. It's a number, it's on the right-hand side. But in some cases, a province might have done something, and there's not a number value out there. So I'll give you an example. Think about allowing not allowing physicians, but allowing pharmacists to give vaccines, right? So how would you quantify that? If you allow pharmacists to give flu shots, that's really helpful. And you might see reductions in your daily flu cases. But there's no way to put a variable like the minimum wage on the right-hand side. So if you have variation in your data that some provinces went earlier in allowing pharmacists to give flu shots, then what you do is you'd code it as 1 and 0 if in a certain year provinces did not allow pharmacists to give flu shots, right? 1, 0. So that's what we call a dummy variable or a dichotomous variable in order to capture the effects of a policy, which is kind of qualitative and cannot be otherwise quantified. And to give you an idea of this is that here we are. I will share my screen again. Here's my Excel sheet, which you can see. And you see the poverty rate, you see the minimum wage. But now you can see in this policy variable, this is a series of 1 and 0s. So if we go back to I just made this up, okay, just to show you how to code it. And whatever this policy is, maybe it's a flu shot policy, you can see that in years which Nova Scotia didn't have that policy from 1990 to 1999, we've coded it as 0. On the other hand, if the policy came into effect in Nova Scotia from 2000 onwards, then it's 1 after that. So let's take another province. Let's say Quebec for some reason, adopted this policy much later. This policy came into effect in Quebec in 2004. So all the values before 2004 in Quebec were 0, and after that, they're 1, so on and so forth. So this is exactly how you would code it, right? A variable like that. Now, this leads to a concept called where is it? There. Difference in difference regressions. So again, I'm running out of time, but I want you to be aware of this methodology. So if you have an economics background, you'll know this. This is the standard workhorse model in regression analysis used by economists when they look at the effects of a policy. So the idea here is that think of a natural experiment, right? Well, not natural. So let me back up on that. So if you're in clinical sciences, what you do is that in order to trust the efficacy of a drug, you give a drug to some people and then you give something which is called a placebo. It's not really the drug, to another group of people who are similar in demographics. So the people who have the actual drug are called the treatment cohort. And the people who do not have the actual drug are called the control. So in the clinical sciences, you can set up experiments where you're clearly demarcating between your treatment and control. Now, as social scientists, we don't have that, right? What we do is we look for, in most cases, natural experiments. Economists are good in running experiments if there's a lot of funds, and you can randomize people into experiments, but in many cases, we don't have that. So what we try to do is when we look at a policy, we look at jurisdictions which didn't have the policy or had the policy later, and we distinguish that from provinces which enacted the policy at a certain time. So in terms of the notation, this is what it looks like, a difference in difference model. And here's the beta 1, which you're looking at. And you're basically creating a variable which tells, which is looking at the effects of the policy when it was implemented in certain provinces in a certain time period relative to other provinces which did not implement the policy at that time. So as long as these policies were implemented somewhat independently, and this is key, independently across jurisdictions, then in terms of terminology, we say that we have a natural experiment. And the best example is to look at what happened in Canada when Quebec introduced universal childcare in 1996. So then you would construct one dummy variable for Quebec, which takes a value of 1 from 1996 onwards and is 0 in Quebec for previous years and 0 for all other provinces. So the idea is that we have a natural experiment in order to assess the effects of universal childcare, because Quebec went ahead and did it in 1996, and no other provinces implemented a similar policy. So then this paper, which was done by Jonathan Gruber and Kevin Milligan and Michael Baker, was published in the highest ranked journal in economics, the Journal of Political Economy, because it is based on this strategy and because we could then look at the causal effects. And it allowed the researchers to understand that after the introduction of this policy, what is the effects on children? What are the effects on female labor force participation, and so on and so forth? This is what we call clean identification, okay? I now unfortunately have only 8 minutes left. So what I'll do is I will quickly cover the other module, which I wanted to look at, and that is looking at survey data. So with survey data, good examples are Canadian Census, the public versions, which are widely used by many researchers. And the difference out here are the observations are not aggregated at the province level, but they're basically based on individual level data. Now, in the previous module, what we did is we looked at when a right-hand side variable is 1 or 0, okay? Now, with survey data, what's going on is that not only do we have a variable which is 1, 0, possibly on the right-hand side, if we want to look at differences in earnings by gender, but when we want to look at the effect of gender on smoking participation, so things become more complex then, because we're looking at large data sets, and instead of the values which you saw earlier on the minimum wage, employment rate, because they're at the individual level, all you see in your data are a series of 1s or 0s. 1, for example, if you smoke or not, and 1, 0, if you're looking, say, at the effects of gender on smoking, okay? So then it's not necessary that ordinary least squares is the best methodology. You can use it, but it's not necessary. So then if you do, you have what are known as linear probability models, but this is now your pathway to machine learning. Data scientists and computer scientists typically use models which are called probit or logit. When the dependent variable, your outcome variable, is either 1 or 0. So the difference is that when you, so I'm not going to go through the regression output, I will just go to the theory. The logit model is based on a particular probability function. I'm sorry the font is so small, but it's the exponent of all your betas and your x's. So if your example is trying to understand why a person smokes, that is the probability of y being 1, you want to use a model like this as opposed to using ordinary least squares, because theoretically speaking, if you use your ordinary least squares, when you do your predictions, it may not fall in the 0-1 interval, okay? And it has to, because you either smoke or you don't. So theoretically, we can demonstrate that. on the other hand, when you use a logit or a probit model, the probabilities are set up with a specific function, which makes sure that when you do predictions, then the prediction does not fall outside 1 or 0. That's why I use logit and probit. And again, it's pretty simple to use logit or probit in R. Here's an example. You use the GLM function, okay? And you just run this, and then that gives you your regression output, okay? So again, it's very straightforward to do in R. And unfortunately, I'm sorry, it just seems I'm out of time, but I hope this gives you enough foundation to go on the afternoon session after lunch. If you think what we've done, we've covered a lot of material. We started off with what is the data point and what are summary statistics. Then we went to linear regressions. Then we went into large data sets, and we went into clustering, and we're finishing with logit and probit. So Elias, I wanted to cover some more stuff for you, but I hope this gives you a satisfactory foundation for your session beginning at 1:30.
Absolutely. We're going to have plenty of material to cover, and hopefully we'll have enough time to do it.
Okay. In terms of quick question, Mohammed, I'm sorry, I won't be able to show you now. I've run out of time in terms of coding and k-means clustering, but Elias, I believe you're covering that in Python. Are you showing them a bit of coding in k-means?
Yeah, we're going to be doing k-means clustering in Python after the break.
Yeah, so Elias will take care of that. And in terms of Mohammed's other question, so in terms of the potential confounders, that's a great question, Mohammed. What you need to do in the difference in difference regressions is that you need to also account for other variables that may impact the outcome variable independent of the treatment, of the difference in difference treatment, okay? So like we did with the minimum wage employment, that doesn't change. Okay, Ethan, we're basically at 12 o'clock, but I guess that we'll give everyone a chance to go for a quick lunch, check email, and I'll be back at 1 o'clock if the learners have some questions.
Awesome. Thank you very much, Anando. Yeah, as Anando has just mentioned, if you are interested in the office hours that he'll be holding, we will see you back at 1 o'clock. If you would like a bit more of a extended lunch break, then we will see you at 1:30 for when Elias begins with his part of the workshop. Thank you very much, everyone. Enjoy your lunch.
And I assure you, Elias is a much better lecturer than I am. So he will keep you awake. He will keep you awake during the afternoon. Have a good lunch, everybody.
Awesome. Have a great lunch.
See you all soon.